Hey, welcome to this video series on Rust, 3D graphics in the browser. My name is Doug Milford from Lambda Valley. We'll be creating this sine wave pattern from scratch, meaning every file and every line of code will be done in this series. We'll be throwing in a few extra bells and whistles like how to move it with your mouse, as well as some shading effects, which helps make the 3D look more realistic. I've posted the final code on GitHub if you'd like to download or clone that for your own needs. This specific video only focuses on boilerplate web setup. The later videos will discuss the actual graphics. Because some of you may not be interested in the web setup so much and just want to cut to the good stuff, feel free to jump to the later videos. The second video will be about us putting some two-dimensional pixels on the screen. This gives me a chance to introduce you to some concepts and terminology and to ease you into graphics as best I can. It's a very complex topic. We'll actually be building this in the second video as a springboard into the 3D video. And then in the third video, we'll be finalizing our 3D graphics. If you haven't watched my previous videos discussing Rust fundamentals and you're not familiar with Rust, please do so. You should have a firm understanding of Rust fundamentals before tackling these videos. This video is not for the faint of heart, so be forewarned. I will be going fast and furious. If you aren't familiar with Rust, I'll lose you pretty quick. There's a whole slew of web technologies we'll be using to host our Rust program. It's only the shell to allow Rust to be used in the web, so don't fret about this portion so much. Once it's set up, we can forget it's even there. The remaining of the program will be in Rust. However, I'm not the kind of guy who likes a black box. If you're interested in learning every aspect, I will be discussing what I'm doing and why for each line of code, even for the web setup. Alright, let's have some fun. Phase 1, Boilerplate Setup and WASM Introduction. You'll need several installations on your computer for all of this to work. That's the state of development these days. A million tiny pieces. I've documented what you need in the README file of the GitHub project, so if you need to reference back to it, it's there for you. I'll assume you have Visual Studio Code and rustup on your computer already. If not, I have a video called rustup set up for Windows if you need help with that. I'm currently running rustup version 1.19.0. You can check which version you have by going to the command line or terminal and typing rustup -- version like so. If you don't have this exact version, you're probably okay, but if you do have issues, you might want to peg it to this version. Since we'll be doing web development, we'll need npm. This is similar to cargo for Rust, except it's for web packages. If you don't have that, you can download it from npmjs.com/get-npm. It will install both npm as well as Node. I recommend you do a local installation, not globally, but either will work. Just follow their instructions. Once again, to check what version you have, you can go to the command line and type npm-v. I'm currently running npm version 6.4.1. Again, other versions are probably just fine. If you have troubles though, you might want to try to peg it to this version. And I can type node-v to get the Node version I'm running on, which is 10.13.0. If you haven't done web development before, you may be thinking, suffering cats, what is all this? Yep, web development is crazier than a grain shipment full of tribbles. But we'll get through it, promise. In my setup video, I had you set the autosave to after delay. I'm actually going to turn that off. The reason being is that it's a little too eager to save, and saving causes our browser to automatically reload. Once you have everything installed, it's time to start making files. I created an empty folder in my repos directory. It doesn't matter where you put it. You can put it in your desktop if you like. And as you can see, my folder is empty. I told you we were doing everything from scratch. So let's open our new folder in Visual Studio Code. We have our blank slate. That's nice. The first thing we're going to do is create a package.json file. This is similar to cargo.toml file, except that it's for the web. With this, we'll be able to easily incorporate certain node packages in our project. Let's import some development dependencies to make this a more immersive development experience via something called Webpack. I'll first need a WebAssembly plugin, or WASM, which allows Rust to be used in the browser. We'll also need an HTML Webpack plugin, a text encoder, Webpack itself, Webpack CLI, and Webpack Dev Server. If I've lost you already, don't despair. This effort will be well worth it, and it's just a one-time boilerplate. Make sure you save the file, and now in the terminal type npm install. This will get all our node packages that we define within our package.json file, as well as their dependencies, and make them available to our project. If you get errors the first time you run npm install, you may try typing it again. If it doesn't work the second time, then you're in trouble. Uh-oh! Assuming you got it to work, the node packages and their dependencies are placed into the node modules folder. It will also add a package.lock.json file, which is auto-generated. This is similar to the cargo.lock file and is not really meant for you to monkey with. Okay, so now we have all of our tools installed. Let's create our index.html file. This is the one and only one HTML file we'll have in our entire application. It's just a shell. If you're not familiar with HTML, no worries. This is literally 9 lines of code for this file, and then we can close it up and forget about it for good. We'll start with our doc type header. Below that, have an HTML tag. It should automatically create the closing tag for you at the same time. And there we'll create a head tag. Then we'll create a link tag. The browser expects that an icon is present. What I'm doing is disabling the error that'll be thrown because it's missing. I guess you could have just also supplied the icon, but Now let's do the body. I'm going to put the styles directly in here instead of the style sheet for simplicity's sake. I'll make the background color black, the margin 0, and as we're resizing the browser, I don't want scroll bars to randomly pop up, so I'm going to suppress those by setting the overflow to hidden. If this were a production application, I wouldn't be putting the styles directly here, but this demo is complex enough as it is, and I don't want to add yet another file. Anyways, we just have one more tag, and that's the canvas. This is where Rust will be doing its drawing. I'm going to give it an ID of Rust Canvas so that it can be referenced by Rust later. There's nothing special about that ID. You could have called it anything you wanted. Okay, that's it for this entire file. You can literally close it up now and forget about it. Now we'll need a web config file to enable WebAssembly, otherwise known as WASM, which is how Rust is able to run in the browser. So let's right-click in the blank space and add a new file called web.config. I'm just going to paste in the contents of this file. This line will allow WASM files to be included in our application. Okay, super duper! Let's close this guy up. We'll also need an index.js file to represent the starting point of our application. Even though this is a Rust application, it still requires JavaScript to glue things together. But don't worry, the JavaScript is minimal, and once it's done, it's done. One main point of using Rust is so that you don't have to live in a JavaScript world. I'm not going to pull a fast one on you and have half of our code in JavaScript, promise. For now, just having the file is fine. We'll add some stuff later. Now that we have some basic files ready, how are we going to actually run this? For that, we'll need Webpack, which is why we included all those things in our package.json file. Right-click on the blank space and create a file called webpack.config.js. Before we begin with Webpack, let me just say that Webpack is an enormous topic and confusing for many people. It's a complex enough topic to fill a week's worth of videos. If this entire section confuses you, don't get discouraged. It confuses everyone at some point. I'm going to discuss as I go, but if you don't catch everything, I'm not going to quiz you afterwards. With that said, let's bring in Webpack as well as the plugin for WASM. We'll also need the HTML plugin and the path, which we'll use in just a second. To configure Webpack, we need to create a function that returns an object representing your configuration. Webpack is expecting to provide two parameters to your function, env, which stands for environmental variable, and args, which stands for arguments. This is how you access certain information you may need, such as whether it's a development build or a production build. I'm going to create a variable to hold whether this is a production build. Development builds are usually much faster to build, but also much bigger, which affects download speed for your users. Production builds are minimized to reduce the time it takes for people hitting your site to have to wait for your application to load, but it takes longer to create the build. This variable will help us make a trade-off decision during configuration. At some point, we need to return an object representing the configuration, which is represented by curly brackets. The first setting we need to give it is the entry point of your application. You might think that's the HTML file, but it's really the index.js file. The / tells Webpack the index file sits in the same exact folder as this file. Other applications may put it in the source folder or src folder, but I'm going to reserve that for our Rust code. Now let's tell it where to output the finalized files. We're going to use the path composed of the directory and then dump it into the dist folder. You could have chosen somewhere else if you like, but this is often the convention. Each file that Webpack produces needs a name. I'm going to do something different based on whether it's a production build or a development build by using an inline if statement. The production version will have a content hash, meaning creating a hash identifier based on its content. Doi. And the development name will have a hash that's based on the actual build. These hashes help the browser know when an update piece is ready and available for a download by the client. Now we need to set up our plugins. The first is the HTML Webpack plugin, which knows how to handle your HTML files. It will take our template file, which is our index.html file, and insert code that will be able to load future pieces such as our Rust code as needed. We'll also need a text encoder and decoder. Firefox and Chrome don't need this one, but Microsoft Edge will have troubles handling strings being passed between Rust and the web scaffolding. So this will shim that up. And that's it. Now, there are a ton of configurations that we can do in Webpack that I didn't touch, but this should be sufficient for our needs. Let's create a script to run our Webpack so that we can see it in action. In the package.json file, I'm going to create a new scripts area. I'll create a script called dev. What I'll be doing is firing up Webpack's dev server, telling it to open it up on port 9000, which is arbitrary. You can pick a different port if you like. If you're running a different project on 9000 already at the same time, this won't be able to start because it's already in use. So just pick a port that's unique enough that it doesn't conflict with your other projects. And I'll use the open option, which automatically opens a browser for you when you run it. Okie dokie, are you ready? Let's run this. Open a terminal and type npm run dev. As a reminder, dev is what we named our script. We could have called it anything we like, but dev is the convention. It will call our Webpack config file to know how to do its job and then bring up a browser on port 9000. Yay! We have a black screen! So let's show you why this is an important result. Webpack is currently watching all of the input files for any change and will automatically rebuild your application and update the browser without you having to shut down everything and restarting. For example, if I modify the HTML page to change the background color to green, the browser will automatically update when I save the file. Boom! Magic! This is called live reloading. There's also something called hot reloading that's even more impressive, but live reloading will be sufficient for our needs. This will come in super handy when we're developing in Rust. As I make changes, we'll be able to instantly see those changes in the browser. Now, normally we have the browser on a separate monitor so that you can have sufficient coding workspace and a full screen browser, but that's kind of tough in a video. So I may be toggling back and forth between the two as we go. Let's set that back to black. To stop the process, in the terminal you need to press Ctrl-C, and it'll ask you if you want to terminate. Just press yes. Okay, that's a simple setup if you want to do basic JavaScript or HTML updates, but eventually we want to be doing our coding in the Rust world. So we need to go back to my Webpack config file and include the WASM pack plugin to prep for that. This file should now be good for the rest of the video, and you can close it and forget it. Let's now create a script to create a production build. I'll reopen my package.json file. As a reminder, a production build is going to be more condensed to reduce the time it takes for your users to download the pieces they need. It also increases the compile time, so there's a trade-off. I'm going to call this script build, which is convention. I could have called it whatever I wanted, like Doug's build, but I try to stick to the convention unless I have a real reason to deviate. To do the production build script, all we need to do is tell Webpack that the mode is production. Simple. Go back to the terminal and type npm run build. If you scroll up a little, you'll see a red error complaining cargo.toml file is missing. Yep, we haven't added it yet. We're close. Before I do that, I want to point out that the build placed the compiled files in the dist folder. Even though we got the red message, it did create our final build. This would now be ready to publish if you wish to. If you remember, the dist folder is where we told Webpack where to put our finished files. This jumbled string at the end is the hash that we applied earlier. The reason that's there is that the browser will try to be efficient with what files it downloads, and it goes by the name. If it thinks it already has it downloaded or cached, it won't try to re-download it. If we make an update to a file, we want the browser to know this has fresh content, so it needs to grab it. If we didn't do that, there's a good chance some client will be running an old code without realizing it. Not good. Okay, let's clean up a bit. Now let's start getting into some Rust. I'll create a cargo.toml file. We'll do the standard package information, name, version, authors, edition. We'll define the crate type as cdylib, which stands for C Dynamic Library. This type of crate will make it so that your Rust code can be used by another language. Specifically, we're compiling it to a WASM target so that it can interact with our web scaffolding. If that doesn't make sense, don't worry about it at this point. We'll need some dependencies. The first is the console error panic hook, which will route panic error messages to the browser's console to give you some information. We'll need JS to bind to our JavaScript's built-in objects. Another thing I'll bring in is lazy static. This will allow us to easily set up some application state. And algebra will be for certain math matrices used in 3D programming, which is great so that I don't have to do it by hand. And last but not least, WASM bindgen, which allows us to glue Rust to the web world. Now we'll need to specify some WebSys dependencies. Don't worry, we're almost done with the boilerplate. I'll set it to version 0.3.4, and I'll just paste in the features. Some are going to be related to grabbing our canvas, handling mouse events, or rendering graphics to the screen. We'll be discussing these as we're creating our graphics. There are many more features we could have included. This is just the minimum setup for our needs. Let's close that up. Just like all other Rust programs, we'll need an src folder or source folder, so I'll create that. And in there, I'll create our lib.rs file. At this point, even though our lib file is blank, we should be able to build it. I'm going to type in cargo build and target WASM, which has this convention. If you don't have WASM as a target on your machine yet, you may get an error. If so, you can easily add it as a target by typing rustup target add wasm32-unknown-unknown. My computer already had it, so it proceeds in grabbing all the Rust dependencies we define in our cargo.toml file and then performing a build. As an example of how to use WASM, we'll set up a simple communication to give you a sense of how the Rust world and the JavaScript world interact. I'm going to create a simple procedure that will print something out to the browser console. Let's bring in our WASM bindgen so that we can use it. This is some prepackaged glue, so to speak. To allow our JavaScript world to see our function, all we need to do is annotate it with this WASM bindgen. So this is now available to the JavaScript world, and we'll see that in action in just a second. We could have set this up as a function and returned a value, but we also have more power than that. I can include functionality in Rust to be integrated with our web world. This notation is going to be a little funky, but I'm going to bring in the console.log functionality directly in our Rust code. That will eliminate the need for us to manually write a bunch of JavaScript anytime we need to log something to the console. This is saying I want to grab something external. What I want to grab is the console namespace, and specifically the log function. Now I can use the log function as if it's native to Rust. This allows us to live more in the Rust world and still have the ability to interact with the web scaffolding. Cool, huh? To continue with this example, let's go to the index.js file and call our procedure. We'll import our Rust program. From there, we can tell it to call our function like so. And we'll catch any errors if they occur and print it to the console. This may seem ugly, but we don't have to manually connect up a bunch of stuff. We'll have a better way, which I'll show you shortly. Now if we run it and open up the console, we can see that our message is correctly printed out. So far this is pretty unimpressive, but it does describe how you can use WASM within your web application, even for non-graphical needs. If you add heavy calculations that need the raw computing speed that Rust can provide, this is how you can achieve that. So without getting too deep, you've taken a big step into the power of WASM. Now that was an example of how to hook up a function with WASM, but we're going to get a bit more involved than basic function calls. Let me delete that function because I don't want it polluting our code. Switching gears, let's talk about our graphical options. There are multiple ways to do graphics in the browser, each with their positives and negatives. The first is SVG. This is relatively simple to learn, but if you're doing heavy graphics, this is going to perform very poorly. Plus, it doesn't have great 3D capabilities that I'm aware of. Because it has such poor performance, and when you're doing large intricate drawings, I tend to discount this right out of the gate. The next is WebGL. The argument for this is that it's going to be much more efficient than SVG in many situations, particularly when you scale up. However, it's not as efficient as it could be. Don't get me wrong, compared to SVG, it's a speed machine, but it didn't quite polish up the performance as much as it could have. For mobile devices where battery power is a concern, it could be a drain. WebGL is very cross-platform, which is a nice positive. A vast majority of browsers support it, around 97% last I checked. That includes mobile and tablet browsers. The problem is that it has a very steep learning curve. Next, WebGL 2 was specifically made to be more efficient than WebGL and better on mobile devices. This too has a steep learning curve. If you're coming from WebGL, much of the same concepts remain the same though. It just introduces a few more concepts to squeeze more performance out of that orange. Unfortunately, the browser support is lacking. One glaring example is that it doesn't work on iOS. Thanks, Apple! That, in part, is why WebGL 2 hasn't really taken off. Without browser support, developers won't develop for it. But there's also another reason, and that's because the next generation in graphics API is coming around called WebGPU. It's extremely efficient because it leverages some GPU hardware improvements that have happened in the last several years. Plus, it squeezes the orange even more to get every last drop of performance it can out of the hardware. Based on some demos I've seen, you only need to expend about a third of what WebGL has to do in order to draw 10,000 elements. That's quite impressive, but there are multiple problems. First, the learning curve is extremely steep, even more so than WebGL and WebGL 2. You really have to know your stuff to be productive. But worse, the browser support is currently extremely poor. Firefox has an experimental feature that's available, same with Chrome. However, they're not full-fledged releases to the public yet. Ironically, I've seen more native implementations of WebGPU than browser implementations. Odd. Because of the significant lack of browser support, it's not really feasible to go all in on WebGPU quite yet. I would love to modify this video to be based on WebGPU, but unfortunately I'll have to wait until there's better support. There are Rust crates that are working towards making WebGPU available, but it doesn't seem that they're quite ready for the web yet. They appear to be more focused on making graphics available natively cross-platform instead of DirectX, Metal, Vulkan, or other native APIs. That's a notable undertaking, but currently it doesn't help us with graphics in the browser. With all that said, based on the trade-offs I've discussed, I'll pick WebGL to get the best cross-platform experience. If you go through the steep learning curve of WebGL, those same concepts are going to be useful all the way through WebGPU. So even if you don't think WebGL is the long-term solution, at least it's a solid foundation to many topics in graphics and will serve you well when you need to jump to WebGPU or some other graphics API. Learning WebGL is time well spent, even if it's not as cool as some of the other kids on the block. You may be wondering why I didn't include Three.js or Babylon or other 3D libraries available in JavaScript. Those are actually wrappers around WebGL. They try to make it easier for the programmer, but there is a performance cost associated with them because they don't have fine-grained control to improve efficiency if needed. Also, I feel I have much more control when I'm using raw WebGL. If I need to do some effect that's cool and different, having direct access to the low-level tools is a must. That said, I'm not against Three.js or Babylon. If you find a decent Rust scrape for those, I might consider creating a separate tutorial. Let me know in the comments section if you'd be interested in that. I'll be discussing what's going on with WebGL while I'm doing it, but I'm not going to go too deep into concepts and topics. If you need a more in-depth training, there are multiple wonderful resources on the web. One I specifically recommend is webglfundamentals.org. Another fantastic one is created by Mozilla, and I actually incorporated some of their training material in my demo. Both are great learning tools. In our index.html file, we had a canvas tag and called it Rust Canvas. We're going to need to wire that up to Rust so that we can do some drawings. In our index.js file, we're going to grab that canvas. The canvas can be used by multiple graphics technologies, so we're going to specify this to be the context of WebGL. I'm going to set up anti-alias to true. What this does is if you have images like JPEGs or PNGs that you want to use, this helps smooth rough edges that sometimes occurs. I won't be using images in this demo. It will be pure math for our drawing, but if I don't set it now, I'll forget about it and images will look grainy once I do add them. There is a performance hit with anti-aliasing. Nothing comes for free, so be aware. You constantly have to juggle performance and quality. Anyways, I'm sidetracking. Okay, when index.js starts running, I want to fire off some Rust code to get things started. At this point, you may be wondering if we'll be doing a ton of stuff in JavaScript like this. So far, we haven't even touched Rust very much. No, this is just boilerplate setup. Once we're in Rust, that's where we'll live. But we do need to do this boilerplate first. Don't worry. I'm going to verify that our graphics layer properly initialized. If not, give the user an alert and exit. I'm going to initialize some graphic settings. The first is blend, which means I want to support semi-transparent objects. This has some performance costs again, but if you want to support things fading in and out smoothly, at some point the item has to be semi-transparent. I find the user experience to be much better when things can smoothly transition in and out of existence, but that's just my opinion. I definitely pay the performance penalty because of it. And I'll set the blend function to source alpha and 1 minus source alpha. Alpha means how transparent it is. There are multiple ways to blend objects if one or both of them are semi-transparent. This one gives something that I feel works pretty well. We need to create a function that will tell Rust when to render. The window renders quite frequently, known as an animation frame. Like a movie, graphics are simply creating a series of images and then flips through them really quickly. When WebGL animates, we want to hook up to that next sequence to render our function. In essence, you're saying on your very next animation frame, I want to call my render function. Once it's done, it forgets about the render function, so we have to constantly set it up again and again. The problem, though, is that this will happen so frequently that we do a bunch of draws unnecessarily. The human eye can pick up about 30 frames per second. For high-speed action games, about 60 frames per second might be needed to make sure everything looks smooth. Movies are typically around 24 frames per second, believe it or not. If you don't control your frames per second, it will run as fast as it can and peg your CPU and GPU sky high. Nothing's more embarrassing than doing a demo and your computer's running at full speed and about to melt down. People look at you like you're an idiot. Believe me, I know from personal experience. Since the human eye can't really see faster than 30 to 60 frames per second, we're wasting a massive amount of resources doing unnecessary draws. So I'm going to be creating a constant that I can set to say how fast I want to render. 30 frames per second is good enough for my needs. We're dealing with milliseconds, not seconds, so that's why 1000 is in the numerator. If I go any faster than that and you look at this on your phone, I'm probably burning your battery for no reason. I also need the last time I drew on the screen. Defaulting it to -1 is fine. I'm creating it outside of the function to create a shared variable for the function calls. It's available in our render function anytime you draw. Let's create the current time right before we actually render. And now let's use that information in an if statement. If it's not time to do all the calculations for our next image, it'll just do nothing. If it's successful, let's update our last draw time to the current time. And this is where we're going to call our update logic and render logic in Rust, which we haven't written yet. The update is intended for you to do calculations to update your application's data. If you have things moving around in 3D space and colliding with each other, this is where you would do that code. The render is supposed to be only for taking your application data and creating an image out of it, a single frame in our movie, so to speak. You might be wondering why you would call them back to back. Why wouldn't they just be one function? Well, first reason is to separate out what each does so that's a clear demarcation. But another reason is that the update can be handled multiple times per render. It's not a one-to-one, although in our case we've set it up to be that way, so technically it's not buying you very much here. In any case, that's what it's for. You'll notice that the render function is slightly dim yellow. That means nothing is actually calling this for the first time. When our application runs, it'll declare the function, but we actually need to kick off the first time somehow. So after its declaration, let's just call it. This will initialize our loop. We're almost ready to jump to Rust, but there's one last thing I want to do before we go here. When someone resizes the browser, the canvas we're drawing on has to be updated. So I'm going to do a quick check whether the height and width don't match. If it doesn't, I'm going to reset the canvas dimensions. The canvas has multiple dimensions that we have to do. So we'll set the height, client height, and style height to be all the same. I'll also do that for the widths. And on top of that, we'll also need to set the GL viewport. I'm not going to sidetrack about what each of these are. This just helps ensure that if the browser resizes for any reason, it'll readjust things accordingly. Let's jump into Rust now. Finally. I'm going to create a struct that will be our game hook in Rust. Why a struct? Because that's what I was shown when I first learned. I believe we could do it without a struct and just use functions, but I'll keep the pattern for now. We won't have any fields for the moment, but we'll add some when we need them. For our JavaScript shell to be able to see our struct, we need to annotate it with WASM bindgen. Let's create an implementation block for our functions. We'll need to define our new constructor, and we'll fill this in later. For now, let's just return the struct. And for index.js, to be able to see our functions, we'll need to annotate our implementation with WASM bindgen. And for it to recognize the new function as the constructor, let's annotate it like so. I'll implement my update function so that it can be called by index.js. I'll ask it to pass in the current time in milliseconds, the current height, and the current width. I'll just return an OK value at the end for now. I'm putting an underscore in front of these variables so that you don't get unused warnings. I'll remove the underscore once we use them. I'll also add my render function. There's no external data needed to pass in here because our application state should already be up to date. Now that we have that up, we can call them both from index.js. Let's create a Doug's client. That will create a Rust struct and we'll have access to its functions and methods. Since our update function is expecting the time since our application started, I'll need to know the initial time. And to get the elapsed time, I just take the current time minus the initial time. So now we have everything we need to call our update and render functions. So let's do that. I'll call the update and pass in the elapsed time, the height, and width. And the render didn't have any parameters, so we'll just call it. That should be the last of the JavaScript code we'll need to write. It's about time. Let's close up the index.js file and forget it. Before we go further, I want to test that everything is hooked up okay. In our new function, let's log to the console that it was hit. Let's run that and see what we get. And there we go. Let's keep it running and also log the update. When we save it by pressing Ctrl S, the browser will reload the program automatically. You can ignore that error message. It disconnected briefly to live reload the code. But I do see our new message. It's actually being hit more often than it shows. If the console sees a message over and over again, it'll just show a count. Let's move the log message to our render. And when I save, I'll see that the message in the console changed too. Now that we have confirmation our Rust code is being hit, let's delete that. And there we have it. Our boilerplate is set up. Nice! I know that was a slog, but we pretty much have the setup done for both the Rust world and the web world. I'm going to do some cleanup so that it's ready for our next video on two-dimensional graphics. Thank you for watching this video. Once again, my name is Doug Milford from Lambda Valley, and I'll see you next time.